So I assume you see a circle with a polygon in it or whatever now, is that right? Let me see, I want to get you guys all bigger. I don't view myself as teaching calculus. I view myself as teaching Marissa and Gabriella and Sydney and Jared, although the subject matter is calculus. And so I like to see your faces as much as I can because your looks of confusion help me to understand I didn't do a very good job. So you don't, we're actually going to get to all this in a sense, but I just want to show you kind of a classic, cool introduction to what calculus is and where it came from. At least it's something I think is cool. And also this will actually hit a little bit of algebra too. But have any of you heard of this dude? Any of you heard of that guy, Archimedes? I think I spelled his name right. No, actually I didn't spell it right. I think it ends with an S. He was one of probably the most prolific mathematicians that ever lived. And one of the things the ancients struggled with was, how are you going to find the area of a circle? I don't know if you've deeply thought about how area works, but for the most part, if you were like me and had kind of a mindless, memorized version of area, you said, oh, the formula for the area of a rectangle is base times height or whatever, and I multiply those, and the answer is 6, and then, you know, -2 because you didn't write down the units, and, you know, that always annoyed you and so forth. But you understand do you understand how important or how simple it is when you get all done with this and you say, yeah, it's actually 6 square inches. Do you understand how important the square inch part of that is? It's not just the annoying math teacher, but you understand that that literally means if you had 6 square inches, that if you put them in here, that would actually fill that up. In other words, when you say square inches, you're literally saying you're covering a surface with squares, and that's the only way we have to find area. Well, if you think, okay, well, let's find the area of a circle, then that's not going to work out so good, right? How are you going to cover a circle with squares? And so this bugged them to death. And they had the term squaring the circle, and what they were trying to do was make a square out of it. And historically, I won't bore you with some of these details, but for instance, that parallelogram is also hard to fill with squares, right? But if you take this little chunk over here and chop it off and then you stick it over here, notice now it is a rectangle, and so you just squared the trapezoid. So you can actually make squares out of all kinds of shapes. And of course, you can do the same thing with a triangle. If I have a triangle like that and I chop it down the middle, and I take this triangle and make another one right next to it, and then I take this triangle over here and make another one right next to it, all of a sudden, you know, triangles can turn into rectangles too by effectively doubling them. And so it's actually not hard, that is the point, to square or make rectangles out of any shapes, well, that are like that picture up there that, I don't know, how many sides does that have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, that decagon. It's not hard to find the area of that decagon, even though we don't have a formula for it. But the problem is, as soon as the side starts curving, you're in big trouble. Like you're not going to make a square out of a circle. Does that make sense? And so enter calculus. So let's do a little bit of algebra here. Let's see, I'm going to go to the center of this thing. I'm so addicted to these iPads because they make straight lines. I love it. So would you agree if I came up with an expression for the area of that triangle right there, then I could just say times 12 and I'd have the area of that decagon. I said times 12, I mean times 10. Decagon, 10 sides, right? It's 10. 1, 2, 3, 4, 5. Yeah, 10.
Kind of like a pizza, yeah?
I didn't hear that.
Oh, I said kind of like a slice of pizza.
Yeah, that's in your background, Andrew. Yeah, so does it make sense that if we found that area, which isn't hard to do because we know half base times height, and then we said times 10, we'd have an approximation for the circle, but of course it'd be too small, right? And so what if I jumped it to not 10 sides, but 100 sides? Did the same math, but 100 sides. What's that going to do as far as trying to find the area of a circle? Chime in. Space bar.
It's going to get you a little bit closer to the right answer, right?
Nice job. It's going to get you a little bit closer to the correct answer to this question, but can we ever get it right?
No.
No. Well, yes is the answer because of calculus. Let me show you. Do you have a graphing calculator? Bust that thing out. We're going to play with it in a second. But let's just do this. And what I'm going to do, because you're good at algebra, right? At least you're supposed to be. Let's make some expressions for stuff. Let's say that our circle is radius r. And what I'm going to show you here is actually pretty hard. I expect you to be able to follow it, but you should start to overheat. Like if there was able to be smoke coming out your ears, I should see smoke coming out of some of your ears here, because I'm going to rely on a ton of algebra and trig that you already know. So the circle is radius r, and let's see. And I'm going to make a right triangle out of this because remember, we know lots of math about right triangles. And I'm going to call this angle right here theta. And the reason I'm calling it theta is, couldn't we come up with the angle? In other words, let's see, 360 degrees in a circle. I broke it into 10 parts. So that means this angle right here is 36 degrees. And so theta is actually 18, right? But remember, what I'm trying to do here is get the area of the circle, which means I'm not going to leave the number of sides of this polygon at 10. I'm going to take it to 100 and 1,000 and 1,000,000. So that theta is going to get smaller and smaller and smaller. And so I'm picking a variable because I want to let it vary. I want to let theta, well, go to 0 ultimately. I want to let n, the number of sides, I want to let it to go to 100, 1,000. And so I'm trying to find a formula for the area for every polygon, not just for this one. And notice I said radius. I didn't say the radius is 9. I didn't say I want to find the circle, area of a circle of radius 9. I want to find the area of every circle. So that's theta. And so now you know how to find the area of a triangle. So I'm going to kind of darken this in over here. The other thing I'm addicted to is colors. Oh my gosh, I can change colors now. It's the best thing ever. I'm going to find the area of that triangle right there. Well, since this is R and this is a 90-degree angle, wouldn't you agree that this side over here, since this is theta, and I don't know, maybe I'll even temporarily give this a name. So I want to know how big A is, because you know the area of a triangle, I need to go base times height. Well, maybe I'll even call it B for base. If I called this B for base and this H for height, then I could multiply those two and say times a half, and I'd have the area of that triangle, and then I could multiply by how many triangles, and I'd have the area of my polygon, right? And so you know trig, you know SOHCAHTOA, right? So you'd say something like, yeah, the sine of theta is opposite over hypotenuse, and therefore B is R times the sine of theta. So that's kind of an important fact here. I sort of now know what my base is in terms of R and theta. And then similarly with H, I could say that cosine of theta is H over R. This cosine is adjacent over hypotenuse. And so then I could say, okay, well, cool. Now I know what H is. H is R times the cosine of theta. And so now I have an expression for that, the two important lengths on that triangle. Remember, base and the height have to be perpendicular to each other, so I can't use the radius to find the area of that triangle. It's not perpendicular to anything. So now I can say the area of that triangle is 1/2 times the base. That's the other thing I love about this, is I realize I don't have enough space. 1/2 times the base times the height. So that would be times R sine of theta times R cosine of theta. Right? Everybody happy? Having fun? Love math. Woo! And now, what do I have to multiply that by to find the area of my decagon?
Times 10.
Almost 10. Because notice I cut my triangle in half. How many?
20.
20. Yeah, so I multiply that by 20. So if this was particular to a decagon, then I could say times 20. But what am I going to say in this case? Because I don't want to limit it to just decagons. What's the larger formula? And this is where I'm going to get the number of sides n involved. Well, that was double that.
2n.
So does it make sense if I go 2 times n, that's kind of my 20 in this case, times a half times r squared, might as well clean things up a little bit, right? R times r, and then the sine of theta times the cosine of theta. And then of course the half and the 2 cancel, so I could say it's n times r squared times the sine of theta times the cosine of theta. Is that the best I can do? So would you agree that gives me an expression? And I'm going to make a lot of math mistakes in this class when I'm teaching this. I shouldn't say a lot, but I'll make some, and embarrassingly, they won't be on purpose. And it's important you understand that, because you're going to make dumb math mistakes all the time in this class. And when I grade your stuff, I want to be able to distinguish between a dumb math mistake and a you have no idea what you're talking about mistake. I'm not really all that concerned about dumb mistakes. You're going to make them on a test. You don't have time to fix them. And I'm not going to take off very many points for that stuff. But I need to be able to read your work. I need to be able to follow your logic and so forth. But, you know, take a chill pill. Who cares if you make no math mistakes? I've taught this longer than a lot of you have been alive, and I'm going to make them. So, well, you should, right? Would you agree that that's an expression for the area of, undo. That's an expression for the area of all, what's the name for that thing? It's not a, there's a whole bunch of them now. It's not 10 or 12 or 20 sides. What is it?
So polygons?
Yeah, poly means many, like polyester, many fabrics.
What you said earlier reminds me of when I was in the Navy. So I was a nuclear tech in the Navy, and they used to say, as long as you understand the concept, we don't care if you got the right answer.
Except unless the missile lands in the wrong town, then maybe.
Well, I mean,
Semantics.
I worked on nuclear reactors for ships, not nuclear missiles, so that's different. We're not shooting missiles or anything, trust me.
So again, in hindsight, you're done with algebra. Like you never need to take algebra again. The fact that we just found a formula for the area of all, and it isn't actually just polygons, they actually have to be regulars. It makes sense. They all have to be the same triangle. You can't say times 10 if they're not all exactly the same triangle. So again, mathematicians have a name for that. It's regular polygons. And so that's amazing, because I actually have a formula now for every one of them. But what's it going to take to get the area of the circle? Like if I want the circle, as one of you said, the more and more sides you have, the closer and closer approximation you get, but it's always too small. But does it make sense? What do I need n to work its way to? What do I need to n? And this is an important expression. Have you ever seen that before? N goes to. What do I need n to go to for this to be kind of a circle?
You want it to go to infinity, right?
Exactly. I need n to get huge. And practically, I could probably stop at, I don't know, 100. If I stopped at 100, wouldn't that be close enough? So if we're just trying to approximate the area of a circle and we said, hey, let's have 100 sides. You can see from 10, I drew this with AutoCAD, there's a lot of space lost out here. So if you're trying to approximate a circle and you choose 10 sides, you're not going to be very close. But of course, it depends on what you're trying to do, right? Are you ordering concrete for something, or, you know, is this an exact? But of course, you know, people like Archimedes, they were bothered by like trying to get the exact right answer to this question. So you really need n to go to infinity, but that doesn't work. Infinity is not a number, but, you know, practically probably 100. I don't have a drawing of it, but if I went to 100, most people would say close enough. All you future engineers say close enough. Who cares about this? And you're not wrong. By the way, I teach engineering 211 and 212. So I'll see the rest of you again next year. And I'm actually more of an engineer minded person than a math person. I like to build stuff. I draw house plans on the side, and I design beams for houses and stuff all the time. And I love that stuff. And I'm more practical minded. I'd be happy with 100, which makes me, I should get fired from teaching math for saying that.
Kind of funny that you say that, because as a mechanic, I used to always complain at the engineers for putting bolts in places I can't get to them. And now I'm going to be an engineer.
Don't forget that.
Right? The amount of times I've cursed the engineers for putting a bolt where I can't get to it.
I'm putting a new gasket on the exhaust header coming out of my sweet old car that I bought a couple months back that I've always wanted, and I noticed exactly what you're talking about. 4 of the, what is it, 16 bolts don't come out very good.
Yeah, it's always that way.
What about the angle? What does the angle have to do for, or what's the angle going to do as a result of choosing n being a lot of sides?
It should decrease.
Yeah, it's actually on its way to 0. So what happens to that expression? What happens to our expression if you take those two? You've got your calculator if you don't remember this, but if you go in there and stick in a 0 for theta, and infinity is not really a number, but you could substitute 999,999, right? Like some big number. What's going to happen to that if you go plug that in? And then the radius would be just a number you chose. Like, oh, I want a circle of radius 9. So think of r as kind of like a constant. But what's going to happen to that expression? And I want you to bust your calculator out. Type in this chunk of it, like 999,000 times the sine of 0 times the cosine of 0. And by the way, we're mostly in radians in this class. So switch your calculator to radians right now. 0 degrees, 0 radians, it actually doesn't make any difference, but let's just be in radians in case that comes up. What happens in your calculator if you type 99,999 times the sine of 0 times the cosine of 0? And somebody tell us whenever you get it done. What's it say? Sweet, here's the answer. Error, 0. Yeah. It says 0?
Yeah, I got 0.
So that's kind of broken. Does that make sense? It's like that doesn't work. And of course, one of the realities is the angle never gets to 0, right? Like it can't be 0 because the triangle doesn't exist anymore. That's why it's saying 0. And so if n goes to infinity, in a sense, what you really have here is a fight. And you should know this from trig, but it's the sine of 0 that's causing the problem. Do you understand that? The sine of 0 is the y coordinate of 0 degrees or 0 radians, and that's 0. And so what you really have here is a fight between 0 and infinity. You have 0 times infinity here. Does that make sense? Who's going to win? Because it's not so much that the angle is 0, it's on its way to 0. And so you have something getting really small, but then infinity is getting really big. And so who's going to win? If I take 0, when you multiply 0 by stuff, it turns into 0. When you multiply infinity by stuff, it gets really huge. And so if you have a tiny number times a big number, who's going to win? And of course, what makes calculus amazing is, turns out there's actually an answer. There's a number there, and it's not 0. And I want to kind of illustrate that with you right now. Well, let me add one thing to our formula. Would you agree that you could actually calculate that angle? We did it a second ago. I said, didn't we say that angle was 18 degrees? Like as soon as you choose n to be 10, don't you take 360 and divide by 2 of those 10s, since there's really 20 triangles that we're describing? And so you have 360 divided by 20, and that's 18 degrees. And so it's actually true then that theta is, well, I'm going to use radians, 2 pi, because that's 360, divided by 2n. And so those cancel. So theta is actually pi over n. And now you have an expression that doesn't have two letters in it anymore. And so kind of here's our ultimate area of all regular polygons as a function of n only. And you know this from algebra. If I say a as a function of n, that's a beautiful piece of language right there. I mean, I don't know how much time you spent hating all the language of algebra, and there's reason to do so. But this is one of the cool ones. In other words, if I say a and n, what that tells the person is, hey, what's about to follow is a formula that will tell me the area, and it's a function only of n. It's only one thing I need to know. As soon as you plug n in, boom, you got the answer to your question, right? And I could say also as a function of r here, because we got to choose a radius, but let's rewrite our formula. So now it's n, actually I think I'll put the r squared in front. It's the radius squared times n times the sine of theta, which we just figured out was pi over n, and the cosine, oops, let's get rid of that. and the cosine of theta, which we also just figured out was pi over n. And so there's kind of our ultimate formula. Now, here's where I want you to do something kind of cool. So setting this aside, what I'd like you to type in your calculator now is just n times the sine of pi over n times the cosine of pi over n. But infinity is not a number, but what I want you to do, and you know how to do this on your calculator, I assume, but you can hit second enter to retype it, but I want you to start out with n is 10. So what do you get for that expression when n is 10? I'm doing this with you to make sure it works. Remember, you got to be in radian mode for this to work now, right? I'm not, so I'm getting there right now. So let's just make sure we all get the same thing. So I'm saying 10 times the sine of pi divided by 10 times the cosine of pi divided by 10. I got 2.9389. Is that what you got?
Yep.
So the fight between 0 times infinity begins. Now what I want you to do is go back and change the 10, hit second entry to retype the whole thing so you don't have to like type that whole mess every single time. And then go in and insert a 0. So make it not 10, but 100. What you just saw a second ago was when we took 99,000 times the sine of 0, it just said 0. But as n goes to infinity, what does this seem to be approaching? I just typed 100 in. What'd you get?
I got 3.1395.
That's what I got too, 3.1395. Now start
Approaching
typing
pi.
bigger numbers. Yeah, type 999. Some of you are saying, hey, that's kind of looking like pi. I'm wondering if it is. So I don't have to insert. I'm gonna go back and change my 100 to 999 to see if it really is approaching pi. Yeah, now I got 3.14157. So what's the answer to something? Do you agree that this is just crazy? And again, we're there, we're done. This is calculus. This thing is on its way to infinity, huge number. This thing is on its way to 0. What's this thing doing down here? Well, think about this, pi over n. If n is huge, what's pi divided by a huge number, effectively infinity? What's just pi over infinity? What's that on its way to as n gets really huge? In other words, 3.14 divided by 999, 3.14 divided by 9,999,000. What's that on its way to?
It's approaching pi.
Not approaching pi.
No.
0?
Yeah, it's on its way to 0. I'm gonna try that on your calculator. If you take 3.14 and divide by 9,999,000, you're getting a tiny number for that. So it's on its way to 0. From the unit circle, what's the cosine of 0? And technically, that should be something you just know. But even if you took that last term, you've probably already forgotten it, right? Which means you have to remake it for yourself. For now, just get your calculator. What's the cosine of 0?
Well, it'd be 0 or 180, right?
If you take the cosine of 0 and do it now, the calculator says 1. You should be able to explain why that is. The end result is this 3-term expression is infinity times 0 times 1. So this is a fight between infinity and 0. And yet, what does it appear that the answer to that is? It appears the answer is pi. And it actually is. Why does that not surprise you that this whole expression up here is pi? Why does that not surprise you, given what your algebra teachers told you earlier in your life?
Because the formula for area of a circle is pi r squared.
The formula for area of a circle is pi r squared. Now, what I want you to notice though is, and this is where calculus comes in, if it makes it to pi, which it appears to be doing, then that means you actually can find the area of a circle. Now you can't make squares out of it, but this is why Archimedes was a genius. He approximated the area of a circle by putting polygons inside it that were larger and larger and larger. And if you let it go to infinity, it actually approaches pi. Well, this is what calculus is about. We just touched infinity. Calculus is about infinity and about limits. Now you might argue, if you're a real mathematician, how do you know it actually goes to pi and doesn't go just a little beyond? We'll save that discussion for, well, chapter 2. But you can get lost in this world, like the concept of a limit and whether something approaches it. And, you know, mathematicians are not content with busting out their graphing calculator and saying, hey, it looks like pi, good enough for me. Engineers are, people like me are, we're good enough. Hey, it looks like pi, let's move on. Beautiful hike, let's go. But mathematicians are more proofy, you know, like they want a proof that that's actually is pi somehow. And we'll get into that a little bit in this class. I'm not going to go too deep into that because, again, lots of you are wanting to study veterinary medicine and you don't need to prove that this is equal to pi. So I want to
just curious though, Doug, like how big do you have to go to get anywhere near the number of pi, like 20, 30 digits?
Well, I just went to n is 999 and I got 3.14157. I have embarrassingly pi memorized out to 5 places and it's 3.14159. So that's tenths, hundredths, thousandths, 10,000ths. I'm off by 2 100,000ths when there's only 999 sides.
So exponential.
So it's massive. Like we're already ridiculously accurate with only 999 sides. And you can kind of think that makes sense actually, but you're always going to get an answer that's too small. Do you understand that? Because we're trying to approach it from inside. We're never going to reach it. Well, we do reach it if n actually makes it to infinity. And so it is important to add to this statement. Calculus teachers would say as n goes to infinity. You can't say that whole expression on the right is pi unless that n actually goes to infinity. If n makes it to infinity, then this makes it to pi. But of course, infinity is not a number. And so smoke comes out of your head. Like this is what calculus is. As most of you said and agreed with earlier on, and I asked the question, can we ever make it to the answer to the circle? And your gut reaction is no, it's always too small. But in calculus, you make it to pi. You get there because we touch infinity in this class. And so that's kind of neat. I mean, you agree with that? You can appreciate that, you know, mathematically minded people, don't forget that Archimedes was like scratching in the sand with a rock, like to do this. And we're sitting here cheating with this ridiculous machine in front of us. I mean, he would have killed people to have something like this. So we're like cheaters. We're getting a helicopter ride to the waterfall relative to what that guy endured, which is kind of cool. When I look at stuff like this, I think I'm not the kind of person that was going to get lost in finding limits to things. I get a little bored with that, and I don't need the proof. Just getting my calculator and seeing it approach this pi is kind of enough for me, which makes me not a true mathematician, more of an engineer type. But that's pretty darn cool. I mean, isn't that a good idea? I mean, I never would have thought of that. Like, let's approximate it with a polygon. That's pretty cool. And so what I just showed you about pi at the end there, that's kind of what chapter 2 is about. And it's just such a terrible way to teach calculus, to bore people with the theory of limits before you actually get to calculus. And so we're just barely going to cover the tiniest amount of chapter 2. I'm not even going to give you a test on it. There's a big part of me that just wants to skip that chapter entirely because calculus really is a cool subject, and the introduction to this kind of ruins it for people. And I don't know, I won't go into that, but so that's just kind of a sneak peek of what it does. And so, and I give this example because it illustrates a whole bunch of things, which is one, I bet I went too fast for lots of you with respect to the algebra I did there. And that's kind of what it feels like to take calculus. Like you actually got to know all the stuff that you're supposed to know. And you'll have to go watch some Khan Academy videos about how to find the area of a triangle and how trigonometry works, because you realize, oh, I don't really have this on board like I should. That'll be a part of this class. Asking me questions about it. That's a part of this class because you don't know your algebra well enough to really take this class in. The second part is, this is something that you were told. I don't know, when's the first time you heard area of a circle is pi r squared? I obviously don't, I remember the day, but like, was it 10th grade, 8th grade? Like
Middle school?
Middle school? That's I don't remember. Yeah, middle school. And of course, you were just told it and you went, okay, and then did some problems, right? And that was because they were teaching you your first look at algebra. And of course, the area of a circle being pi r squared is really cool because the r can be anything. As soon as you throw the r in there, now you can find its area. And the only reason it was right to you is because the teacher said it was right. You could have came out with 590, and if they said it was right, you would have went, all right, I got an A. But it's like, wow, that was a lot of, it actually took calculus for you to get that little piece of wisdom that you got as an 8th grader. And it turns out you don't need calculus for almost anything. There are some examples. You'll need it in engineering. But it's actually more of a way of thinking, because most of what algebra has done is actually given us all these formulas that we use for algebra. I use one for beam design that has to do with, if you put weight on a beam, does it make sense it's going to bend down like that? Engineers call that deflection. That bending motion has a formula to it. I won't go into the details because you don't want to know right now, but that bending is WL squared over 8. That's an algebra formula. It comes from calculus. It doesn't come from Calc 1, it comes from Calc 2. But I use that every day. But do I need to know calculus to use that formula? No, somebody handed me that formula. I could have no idea where it came from. I could Google search it. I got the formula. Now I'm designing houses and making my living, and I never even know that calculus was even involved in it. What you're really learning in this class is how to think calculus, and you're also getting an appreciation for how just amazingly cool some of these things are. And I'm going to give you projects in this class that give you a chance to get your hands on some of that, and that's what makes this class beautiful. But most of the time when I'm out and about, people ask, what you do for a living, and I say teach math, and I'll say things like, oh, I'm teaching calculus right now, and they'll say to me almost invariably, I took calculus, I got a C, I didn't understand it, and I don't need it. That's what they say. And that's because you don't. You're not going to need to know how to take the derivative of x cubed, which is what we're going to do in this class, in order to be a veterinarian or even an engineer. But it's still cool. It's worth looking at, and it does give you a way to think about things, and it does give you the ability to build these formulas for yourself. And keep in mind that the sum total of what people need to know is not done yet. Like, there are still people figuring stuff out right now. So bear that in mind. Anyway, in that ramble, let's start now with the last little bit of time we have, just kind of reviewing some algebra stuff. And tomorrow, we'll just review algebra stuff. And we could spend, any amount of time on this. We could spend weeks and it still wouldn't be enough. But I at least want to just get your juices thinking again. So let's just talk about this guy right here, this parabola. And I'm going to use the language of algebra. Instead of saying y equals, I'm going to say f of x equals. Let's look at this expression for just a second. So you should remember, yeah, that's a parabola. That's got a curve to it. That's kind of cool. If your algebra teacher did a good job, you even know that that's the shape of a satellite dish. And that's probably the reason we're even meeting like this right now, because that signal is able to be cast through a satellite dish. It's the reason you have a television signal to watch Netflix at night. So, that's got some genuine applications, really cool stuff. It's the shape of something flying through the air. If you throw a projectile through the air, it flies in the shape of a parabola. So your ability to kind of model celestial travel and stars flying through space and comets and things like that, it's all based on this. And so cool stuff. Can you, one, demystify this statement right here? If I say, what is that? Can you explain, although that looks really weird, could you explain to somebody that's just barely learning math, that's not that hard. I mean, it looks weird, but what's that person want to know?
Well, f of x is just saying if f is a function of x, what does it equal? So that would be x equals 2 in that scenario, correct?
Yeah. And really, this is a description of one particular parabola. There's thousands of them, ones that are going up and ones that are skinny and ones that are fat and ones that are upside down. This is one point on that parabola, and you're being told x is 2 and you're just being asked for y. Like, that's all this is saying. This is not complicated, right? So I plug 2 in there. Of course, you can kind of do that in your head. 4 minus 8 is -4, minus 7, I think it's -11. And so all this is really saying is there's one of your points, and if you want to graph it, keep doing that 100 times and you'll have enough points to kind of make the actual parabola. But keep in mind, if the parabola is a satellite dish, does it make sense these are also dimensions? Like, if you actually want to make a satellite dish, you need this math in order to produce one. It's not enough just to say, and I could have done this if I said, hey, what's that right there? And you said parabola. Yeah, because you know what I mean, but that's not a parabola. It's not going to do a parabola's job, which is to take a signal coming in and bounce it off and get them all to focus at the exact same spot. That doesn't actually work unless it actually is a parabola, which means you got to take some dimensions. You got to make it correctly. So that's not that complicated. We aren't going to do this, but what's this person want to know?
Y equals 4. What does X equal?
Yeah, this is a dumb way to make points. If you choose Y first and then you say, what X's do I get? And you notice I said X's because there will be 2 of them here. Well, there could actually be none because maybe the parabola never makes it to Y is 4. I just made that up. But you got to use the quadratic formula to solve that now, and you're going to get 2 different answers, right? So there's actually 2 points that have a Y value of 4 potentially. And so that's kind of dumb way to find points. But again, you should be like, oh yeah, quadratic formula, got it memorized. It's already sitting inside my graphing calculator. There's a program in there. I just type in 4, boom, out pops the answer. Like, to get calculus, that's how you have to kind of be able to think like that. That's gonna come up in this class numerous times. If you don't have a program in your graphing calculator, we may have a little side discussion about that at some point, or you might want to go online, but we're not going to waste any time talking about the quadratic formula in this class. It's just going to be assumed that if we ever need it, if it's one of our tools to do some calculus, we're going to just grab it and get the 2 answers that come with 4 and get on with it. And so, you know, again, it could be that although you should know that, the answer is, well, you know, go watch a couple videos. Turns out we're going to make a lot more use in this class of this. This statement right here is actually Calc 1. Now, what I want you to do is be able to grind out the algebra, and we'll talk later about why this is cool. I'll hint at it a little bit right now, but this is not just a random statement. But keep in mind, this statement up here is not complicated. In other words, this 2 could be a star, it could be a rabbit, it doesn't make any difference. It's like whatever you put there, it just means put it here and put it here because there's a couple X's, right? So this is no different. So somebody decides to stick in something weird, like not even a number, but like some weird expression. Well, is it that hard? It just means put it here and put it here. So I'm going to carry that out right now. So, okay, well, you know, whatever's in here, I'm squaring it, right? So I got to square it, and then I got to -4 times it or multiplied by it. And then there's a -7 that kind of, the -7 doesn't care, right? That you put X plus H in there. And then again, you should be able to simplify that disaster really quickly. And when you took that kind of stuff, back in Algebra 2, you might have been just bored to death and like, you know, why do I need to know this stuff and what good is it? And like, these are skills that we're going to use in this class to see some pretty cool things. But again, I just have to assume you can pull this off. And I hope you're not this guy that thinks this is the answer. What 2 dumb mistakes is this person making that you should not be making anymore?
Didn't FOIL the X plus H.
Yeah, you don't know the distributive law for X plus H. There's more to X plus H times X plus H. You're screwing up the distributive law. What second dumb mistake is this person making?
You didn't carry the negative to like -4H.
Right, Sydney. So they're actually both just the distributive law. It turns out your algebra mistakes there's only a few algebra mistakes to make, and distributive law is like 90% of them. And so, no, this is really X squared plus 2XH plus H squared minus 4X minus 4H minus 7. And of course, you can clean that up a little bit, or can you? I guess you can't. You're done. There's nothing there that you can collect together, right? And so that just looks like, you know, utterly kind of boring practice and so forth. But it turns out that's going to give us something really cool. And let me give you a hint at where that's going. And so would you agree that in previous classes you talked about slope of a line, but you never talked about slope in this context? Why not? Well, because if you're here, and think of this as like you're in a half pipe. If you're an X Games kind of person, you like slope is a thing, right? It's not very scary to be down there and sort of let yourself go, because the slope is effectively, if I kind of draw that tangent line in there, that's your slope at that point right there. So if I'm skiing down this half pipe in this direction, I'm sort of not terrified. If I'm at that point right there, because the slope is pretty flat. Whereas if I'm up here, then the slope is much steeper, and maybe I am terrified to start from right there, right? Would you drop into that half pipe, so to speak? Would you be terrified if you're standing on the top of that? It's 18 feet tall and you're just learning to ski. So like slope's a thing, but the point is the slope is a thing in this world too. And it's actually way more of a thing here than it is here. That's like boring. Like how many times are you in a place where the road just holds the same slope the whole time? It doesn't do that. It actually undulates a little bit. And so what we want to be able to do in the real world is talk about slope or rate of change in all kinds of environments. And so we need to actually be able to find the slope of that curve right there. And we'll get into this in chapter 3. This is the next time we're going to see this mess right here. But it turns out that math that we just did right there, we're actually going to be able to find the slope at that point. Now, let me give you another quick hint about calculus. Would you agree that if I wanted to find the slope at this point, that's actually not that hard? I could just find another point that was pretty close to it like that, and then find the slope between those 2 points, which you remember how to do from previous classes. And it's like, isn't that an approximation for the slope right there? And as I said before, isn't that good enough? Like good enough. Like I just want to know how steep it is there. Isn't that close enough? Yeah, for all but real mathematicians, that's close enough. But if I really want to know the slope at this point right here, does it make sense that I need the second point to be really close? Would you agree that effectively this second point is going to make my slope always too steep? Because if that second point, I'll redraw it up here, does it make sense if that second point is that far away, I'm getting too steep of an answer? But the more I move that second point closer, the slope is kind of flattening out. It's getting closer and closer to the right answer. Well, it would make sense that there actually is a slope right at that point right there, but I could never do it because if those 2 points are the same point, if this is the point 1, 2, and then that second point up there is so close that it's the same point 1, 2, well, now what's going to happen when I try to find the slope? Well, I go y minus y over x minus x, and I get 0 over 0. And so it, like my little plan sort of breaks, right? So I can't, that doesn't work. Well, as I just hinted a minute ago, how close do we need those 2 points? Well, we needed them to get infinitely close. And they can get infinitely close, and we're actually going to get an answer to this. It isn't going to explode. We're actually going to get the slope at that point. We're going to literally let those 2 points become the same point, because in calculus we can touch infinity. In order to algebraically do this, we're going to have to carry out disasters like that expression right up there. And I won't steal my thunder for later and go any further with that, but it's like the calculus side of this is actually pretty simple. But can you do this really quick then? Like, and so it turns out that Calc 1 is finding the slope of a line. Like one of the things I always jokingly say when I teach this is like, don't tell other people, but that's all we're doing in this class is finding the slope of a line. I'm just going to give you 2 random points, and so therefore this will be kind of messy. Can you still do this? If I give you 2 points, and of course we could do this back on this parabola back here, and I could pick a couple of literal points on this. As a matter of fact, I think I will. It sounds like it'll be more fun. But I'm not going to take the time to make this up to work out kind of nice for you. To save a little bit of time, because we're going to run out of time, I'll pick the one we already did, which is f of 2, which we already said was negative 11. And let's choose the other point to be f of, I don't know, negative 1. So if you plug negative 1 in, you'll have 2 ordered pairs, and then can you still find the equation of a line from that? I'm going to give you, I don't know, a minute or 2 to play with this. We're at 9:20 right now, so I'm going to give you like a minute to play with this. I'm going to quickly do it, and then we'll be done for today. There's the equation again. I forgot you couldn't see it. I got -2 for that. That's what you got. Is that the 2 points? So we're going to find the slope through those 2 points. So slope is y minus y. I like positive numbers, so I'm going to subtract that direction over x minus x. So I get -2 plus 11, which is 9. Yes, I'm living right. I got a whole number. That's so lucky. So I got a slope that wasn't a fraction. That's really lucky. You guys got lucky. The 10 o'clock class is not going to get that lucky. You guys deserve something for waking up at an 8. Cheers for you. And you remember that the equation of a line is y equals the slope times x plus the y-intercept of that. And I hope you don't see this as like step 4 in the process. I mean, the fact that the slope goes there in the equation of a line is a really cool discovery that somebody made. This gets taught really boring in a memorized way in an algebra 1 class, but the reality is don't these points have to work in the equation? In other words, when I put in x is -1 and I put in y is -2, this actually has to be equal. Well, that's how you discover the point that's missing. That's logic. That's not step 4. Like, think. So you should be learning a lot of algebra in this class, learning to think more deeply about stuff you already knew and forgot because you just mindlessly memorized it and didn't think it through. That technique is cool because it works in all kinds of situations. Well, let's see. -1 times -3 is 3. So in order for that to be -2, then I guess this has to be -5, right? So for me personally, I'm not done yet with this question because I probably made a math mistake someplace. You know, it's supposed to be y minus y over x minus x. I could have got that upside down. I'm subtracting negatives. I could have done something stupid there. I mean, there's just all kinds of things I could have done wrong. Did I do anything wrong? Is that what you got? I probably didn't give you enough time. Is that right? Now, one thing I could do is check the other one. Since you're not answering, I'll have to check myself. You're supposed to help me, but you're not.
I'm still trying to keep up. I'm a little tired. This is a y equals mx plus b, right? That's the equation you're using.
Yeah. Actually, I'm thinking I got it wrong because I'm using the other point, 2 -11, and I put 2 in for x, and I get -6 minus, oh, it is right. -6 minus 5 is -11. So now I think I got it right. Now I'm done because I checked my work and I didn't do anything dumb, which is a miracle. And so I found the equation of the line that goes through those 2 points. So let me show you something really quick. What was that equation? Y equals, was it x squared minus, tell me if you remember this, minus 4x minus 7, was that it?
That's correct. I wrote it down.
And then we just got the, have you used Desmos before? Desmos is amazing. Like, you're going to be able to use this on a test. So it's way better than a graphic calculator. Anyway, we'll talk about that as it arises. So then I just got done with this problem, and I think it's -3x minus, what was it? -5? -5. So does that go through the 2 points that I was indicating? Let's see, one of them was 2 -11, right? So, hey, look, it works. Like in this class, you should make algebra mistakes, but you should be catching them yourself. There should be a physical reality behind this. You should be looking at a graph going, yeah, look, the graph actually works. Does it go through the other point, which I definitely can't remember? -1, -2. I just want to see them, so I'm kind of slow. Slow enough that I can't find the comma. So it's like, look, it worked. We found the slope of the line through those 2 points. Would you agree that's an approximation for the slope at the point -1, -2, but I'd have to move that green point closer to it for this to work. So we need to know these kinds of skills. Like we've been able to find equations of lines just super quick. Something else we'll do in calculus, what's the area of that shape between the line and the parabola? Would you agree there's no formulas for that? Like you don't, oh yeah, I learned that in algebra 1. You don't have a formula for that. With calculus, you can actually find that area. And I don't mean approximated, I mean perfect, even though it's not even a circle. Like you have a formula for a circle, but you don't have a formula for all the other curves that exist in the world, like sine and cosine and all the other curves. We can find the area of anything. That's Calc 2. So that's kind of some of the practical side of this. Like I have a front yard, I need fertilizer for it. It's some weird bean shape or something. Like you can find the area of stuff like that using calculus. It has a practical side. But you can see what I'm hinting at, and I need to shut up, but you can see what I'm hinting at, which is you need to know algebra to do this. The principle behind, hey, I need to find that area, or I need to find this, the equation of this line, that has to be easy. So practice. So you should jump into my open math. All of my assignments in my open math are not due till the Sunday after we talk about them. And so the algebra review assignments that are in there aren't due till Sunday night. If you're dumb, you'll wait till Sunday night to work on them. You'd be way better off to start right now, because tomorrow we could start the class and you could say, hey, can I ask a question before we start? I was struggling with question number 7. Could you give us any advice about that? And then I'll do it. Whereas 10 o'clock at night on Sunday, not going to be so successful. So get into my open math, get started on that assignment, start plinking around in there. You got 3 tries for everything. So you can get it wrong once and try it again or whatever, which is good because you're going to make algebra mistakes. But launch into that stuff, kind of get yourself going, make sure you got the syllabus all set up, ready to roll. So tomorrow we'll just ramble about algebra the whole time and get after it. So sweet. As I said before, don't teach again till 10. So adios if we're good. Otherwise, stay after and we'll have a little more chat. Nice to meet y'all.
Thanks, Doug.
Anybody else have a thought? Raise your hand.
Hey, so I just have a couple quick questions.
Go ahead, Andrew.
So I have a 5-year-old. So he starts class at 8:30 in the morning, obviously, because nobody can go to school right now. So by 8:30 every day, I kind of got to interrupt whatever. I mean, I'm not going to interrupt you, obviously, but I'm going to step away to help him get his class going. I don't know if that'd be a hassle or anything like that.
No, that's what I mean. That's take care of business. I'm expecting to be teaching people like me that have lives. You know, I got texts coming in about house plans I'm drawing, and I'm not sure I'm getting paid to be here. So just pop back, what you need to do, pop back in. I'll post the notes afterwards so you can get whatever you missed or whatever. And you can totally get it. I expect you guys to be in the middle of it, and you're more than welcome, like after class is over, to say, sorry, I checked out for 10 minutes there and I missed something. I could say, you know, I could say, well, I'm going to say after, not the question.
Yeah, I mean, and you say you're recording too, so we can always like go back and check over what I missed. I just want to let you know ahead of time, like if I just disappear at 8:30 for 10 to 15 minutes every morning, that's what I'm doing.
Yeah, I appreciate you.